welcome you to the thesis defense for Devin B. Farrell. We got the wrong Devin in here a minute ago on our forms. We have the right one now, so we're pleased about that. I'd like to begin with an opening prayer, and then afterwards, Devin, we'll ask you to introduce your guest.
Okay.
That's Paul.
Our dear Heavenly Father, we're grateful to be here to be a part of Devin's thesis defense. We're thankful that he's been able to get to this point and to do the research that he's done. We'd ask that thou would bless us with thy spirit and help us to be able to learn new things from Devin and bless him to do a good job on his presentation. And we say these things in Jesus Christ. Amen.
Amen. Thank you, Paul. Well, it's been a pleasure to have Devin here. He's he arrived a year ago last September.
That's right.
From BYU, Idaho. And it's been terrific to have him in the lab. So what I'd like to do is I'll have you introduce your guests.
Okay.
Okay. And then we'll have Devin give a presentation. This will be the public part of the presentation. When that's done, there'll be a chance to ask questions. And we'll let that go on as long as there are questions. After that's done, we'll excuse the audience except for Devin. And we'll visit with him with the committee. Then we'll excuse Devin while the committee deliberates, and we'll invite him back in and announce the results of the deliberations. So, any questions?
No.
Okay, so how about introductions, and then you can just launch right in.
Okay. I'll just start with Quentin. That's Quentin, Peter. There are two PhD students in the lab. My lovely wife, Eloise. Brian, he gave an excellent example for me 2 days ago. Paul, Eric, and Polly. All of these people of which have helped me out a lot along this process. And so I'd like to present my thesis as the development of principles and criteria for the design of laminate immersion mechanism flexures with specific application to metals. And especially I'd like to recognize my committee who are all here, Dr. Magleby, Dr. Todd, and Dr. Howe. First off, I'd like to just establish my overview of what we'll talk about today. First of all, the first item we'll discuss is a limb flexure performance criteria. Next will be the development of two new novel limb flexures that are suitable to metals, and the application of these limb flexures in a mechanism. So first of all, I'd like to discuss what laminate immersion mechanisms are. We're all very familiar with compliant mechanisms, which transfer force and motion through the deflection of flexible members. Laminate immersion mechanisms are a subset of compliant mechanisms that are manufactured out of a planar material and then function out of that planar application. And I have an example of a laminate immersion mechanism here that was built by a previous student. It's a 4-bar mechanism. As you see, it urges out of the plane. I put the specific force on it, and I could pass this around. I know we've all seen it hundreds of times before. It's a very good example. Next, I discuss a little bit about past research, what's been done before. The material are the limb joints that have been made have been specific for materials more like thermoplastics and papers. Right here you see a limb joint, or a leg joint, developed by Joey Jacobson. And these materials that I mentioned have been used as learning tools or building blocks to the ultimate goal of material to be used, which is metals. And the reason why metals have always been the goal in mind in limb research has been because of, first of all, of their low-cost manufacturing processes that are inherent to sheet metals. These are things as stamping, linking, and so forth, where you could theoretically build an entire mechanism with just one stamp. And also the metals have unique mechanical characteristics that are very useful. Well, first off, there's no delamination, which is something we see in paper. It has a high melting point, has a good formability, which allows a new dimension which hasn't been looked in before to creating limb flexures, which are limb joints, which we will talk about next. Low susceptibility to creep, of course, which is important in combined mechanisms in general. More predictable fatigue life and higher electrical and thermal conductivity. Some challenges, just to list a few, are that metals have relatively low elastic range, which is an issue in combined mechanisms. As you can imagine, material cost is sometimes, are very often more expensive than, say, your regular plastics or papers. And also weight may also be an issue, because they're definitely more heavy, or heavier than other materials on average. So since we are talking about limb joints, let's talk a little bit about the difference between distributed and localized compliance, or what's sometimes called lumped compliance. So we have two beams. They're the identical lengths on both sides. One has no flexion, one has a flexion as example there. And both have the same force applied. And flexure allows a greater deflection in this figure than the one over here, which is a great benefit. And so let's discuss some other potential advantages to using limb flexures. One is approved off-axis stiffness ratio, which we'll talk about in detail later. But this basically describes how well the flexure would, or the joint would behave in multi-axis loading. A smaller overall footprint. You can imagine if we were to keep the thickness of this one and the width constant to this one, we'd have to make it longer to receive the same deflection that we get with the joint. There's also a potential to increase the optimization complexity with topologies because we have more options of creating deflection. These options could be, we could have a joint specific to torsion, bending, spherical application, and so forth. So even though I know I've been intermixing these two words so far, but previous research in limb joints has been specified limbs as joints, such as the lead joint. However, in metals, there are joining processes between two pieces of metal that are very well known, such as lap joints, butt joints, T-joints, and so forth. So to eliminate any confusion, in my research, I have referred to these joints as flexures. So let's look at a little bit of terminology and kind of the process of how limb flexure is made and how we can use metals, the formability of metals to help us out there. So first we have a lamina, then in the lamina we cut out a limb member. We can create a flexure through removal of material, which has been the past research, or the new research in the metals can branch us into forming, or you can use a combination of those. Now, in flexure design, a good question to ask, what are we trying to do? What are we trying to improve from? Do we have a baseline that we can look at while we're designing these flexures to see if they're good flexures? So I've developed a concept of a benchmark, which is a strip of limb member that is the same overall length, width, and thickness as a limb flexure, as you see example there. And we'll use this more extensively later as we talk about the limb flexure criteria. So viewing all these things and knowing that there is a baseline that we have that the limb flexure should improve on, there's three criterion that have been developed to describe this improved performance. First of all, it would be very nice to have a lower stiffness, a higher flexibility, brought by the limb flexure over the benchmark. Also, larger maximum motion, as we talked about before in the figure that we showed. And improved off-axis stiffness. And this figure here, as we see, we have a door that just has a bend in the middle. So it's just that the material itself is bending to create the motion. And it's bending under this moment, mz. And the stiffness caused by that moment is kz. Now stiffness is along the other axes, which we wouldn't want the door to deflect around, as ky and kx. Now if we compare this door to a rigid door, the box is highlighting the comparison, the points of comparison. We can easily see that this ratio of the undesired axes of deflection and rotation over the desired will definitely be greater with the rigid joints. So we see an improvement. And so we would like our limb flexures to have similar characteristic in that their design axis of rotation is improved over the other two, or if it's multi-axis, other one, or how whatever have you. So let's look at the first novel limb flexure. This is the Revolute U-form flexure, as you see figured there, in the undeformed and deformed positions. The concept of this flexure was brought about by a research paper by Dye, and where he described how you could model a die crease in a piece of cardboard as a Revolute flexure. So here, let's look at kind of theoretically what this joint does for us, or should do. We have the material property dependence and the geometric dependence. The material we won't discuss here, but let's discuss a little bit about the geometry. The rough is designed to be formed through stretch forming, which causes this length, this preformed length here, to stay the same. That's why it's encased in ice, because it's held constant. Which causes the length to increase locally and the thickness to increase, which causes, going by the equation we have there, the deflection to increase also. Also, we find that through decreasing the width will also decrease the moment of inertia, thus increasing the deflection. So the closed form solution we used was I used a Castigliano's theorem, which was the partial derivative of the strain energy over the force within the rough joint. And I also created a finite element model with ANSYS being 3 elements. And the elements in the middle, where you have the curved portion where the slots would be, I just modified the material properties for those beams accordingly. And applied a non-follower force, the fixed placement on the end. And the reason for those specific boundary conditions was the test setup that we had available to us to test this joint. As you see there on your right, it being tested in the test fixture with a load cell gathering the needed data. And I have the actual physical prototype here. I'll also pass around of the rough joint. So let's look at some force deflection results, and compare those results to the criteria. First of all, even though this is force deflection, I'm also showing the material yield. So we have the force deflection curve up to the point that theoretically the material should yield on both the benchmark, which is shown by the red, and the rough, which is shown with these 3 models. First off, we can notice that the prototype data matches very well with the FEA. So let's look at the criterion. First of all, does it provide a lower stiffness? Well, if we look at the force deflection curve, we can see that the stiffnesses are different and the rough is lower. Also, maximum doesn't have a larger deflection for yielding. It does, as we see, it's very apparent. Also, I made a non-dimensionalized plot of the data given in the previous plot. And fortunately, we also see a difference in slope the way that we like to see. So off-axis stiffness was also calculated with the stiffness of the torsion, the torque axis over the stiffness caused by a moment. And so in this instance, the higher the off-axis stiffness ratio, the better. So the blue line representing the rough is indeed better than the benchmark cutoff, again at the yield point. So we see an improvement in off-axis stiffness ratio. So now we discussed the rough. Let's go over the tough joint, which is a torsional U-point flexure. And this one is design specific for torsion. And as with the rough, let's look at some of the things that make this joint ideal, or flexure ideal. So as we decrease the width here, even though it's not as easy to see in this equation as it was in bending, this is a torsion equation here. We have a decrease in width, and that would cause an increase in rotation. Also, the decrease in width would...
Could you go back to the previous slide?
Yes. The polar moment of inertia. So this decrease in width would potentially create off-axis problems in bending. So to eliminate that anticipated problem, I designed that there would be a profile form, a round profile form for the joint. So I created a finite element model with ANSYS shell 93 elements. And that's some of the boundary conditions I used. I fixed at one end, made this end infinitely stiff, and set some boundary conditions at these three key points. The two on the edge were set so when torqued, the model wouldn't compact in the y-axis due to...
Wouldn't pull in, right?
Yeah, wouldn't pull in, exactly. Looking for the right word. And here, the translation in all three axes were fixed. Torque was applied to create the motion that we wanted. And here we have the testing of the prototype in the Instron with a torque transducer that was used to get. What we see here is the torque rotation curves. Again, we have benchmark and two solutions for the tough. The data compared between the prototype and the FEA very well. So let's look at the criteria. First one, you do see a difference of slope, not as much as with the rough, but it is a difference. Especially the closer you get to the yield point. There is larger rotation before yield. And with the tough, we did a little bit of a generalization of the dimensions. So this first plot here shows a ratio of the maximum rotations at different ratios of length over width. So as we go from 0 to about 13, well, from about 1 to 12 values of the ratio with the thickness held constant. So here we have kind of flipped where we have the same y-axis, but the thickness is being varied and the ratio of lengths to width is held constant. And these plots show with the arrows that as long as the ratio of maximum rotations is above 1, then we should be pleased with the performance because it will meet the criteria, meaning that the maximum rotation of tuff is greater than the benchmark. In this situation, we're comparing the slopes in the form of stiffness, where the ratio of stiffnesses should be less than 1. And we have the same situation on the horizontal axis as before. So let's look at the off-axis stiffness ratio for the tuff. Here we find that we do indeed have an improved performance, off-axis stiffness. Primarily, I think that you would agree to the profile that has been formed there. So now that we've looked at these two novel joints, let's look at an example of the application of them in the mechanism. To apply both of them together, it seemed to me to be ideal to combine them in a let joint, where a let joint has 4 members that are designed to be put in torsion and 2 that are designed to put in bending. And where there's designed to be torsion, I put the tough, bending, the rough. And came up with what I will refer to as the compound let joint. And with that compound let joint, I designed a basic crank slider with the compound let at those locations. So, before we go any further, I'll show you the biggest prototype that I have here of the crank slider with the compound let joints. I'll just actuate it here real quick so you can see. That's how it performs.
How far are you from the yield point of the material at the highest stress in that position right now?
In that position, as we'll talk about, going by the FEA analysis that I did, it's roundabout yield at that point. And just feeling the resistance of the material when I bend it physically, that seems to be true. So let's look at the FEA model. There's it in the flat position, an actuated position, and I actuated it with a displacement in the middle. A full model would have the one end fixed, the other end translations and rotations fixed in this manner. However, and why I deflected it in the middle was so that I could create a simplified model which would be easier to compute in ANSYS. And I fixed it in this fashion around these axes and these edges to create the desired effect. So they would behave as the full model would. So let's compare the prototype, just visually, to the FEA model, the deflection between both. So that's undeflected, deflected. They look pretty similar. And they are at about the same angle to one another. So that's very good. So FEA results that I ran on this crank slider was on the y-axis. I have the maximum equivalent stress throughout the whole mechanism as it is deflected, or as this angle, as you see illustrated, is advanced. And just as a reminder, this is the compound, the crank slider with the compound let joint and the regular let joint comparison, and we see a 50% increase in motion with this analysis. The summary and conclusions, the following items were successfully accomplished in my research. First, I was able to create limbs from sheet metal, which with a focus on flexures. So even though I did have an application in my research, most of it has been on the deep analysis of these flexures. And also the introduction of a benchmark for comparison, which can be used in the future as a design tool. Also, the establishment of a performance criteria has been set forth based on the concept of relative performance to the benchmark. I have designed and tested 2 prototypes of the rough and tough, which as I've shown, and done analysis of it. Performed an in-depth analysis and shown that the prototype and the FAA match up very well, which had a lot to do with boundary conditions. I developed a crank slider mechanism to apply these elbow joints to. And all this, I believe I had successfully laid foundation for future research in the area of limbs and metal limbs specifically, which will, and also laid the foundation for a research paper that I'm planning to, that Dr. Magley are planning to submit to the Journal of Mechanical Design in the next few days. So some future work that could be done off of this research. First of all, the performance criteria obviously is not exhaustive. It can be expanded to benefit further exploration of certain properties such as fatigue, life, thermal properties, and other design variables that you would be interested in. The performance criteria can also be used to identify design rules for limbs. This would include the ability to design multi-axis degree of freedom flexures, unlike the just single-axis ones that we've seen here. Also, other materials, as in other metals, options between other metals should be explored. Of course, between different metals, there's lots of variability in cost, in weight, and properties, and so forth. So that is definitely an area that could be looked in further. Manufacturing and effects of these manufacturing processes could also be explored and should be. This could be on more of a material science level, looking at the effects of changes in grain boundary, which would cause things like word hardening and so forth. Also, further applications of the limbs should be continued, which is the umbrella goal that we're shooting for with one application. So I'd like to acknowledge in my research, first of all, the National Science Foundation, who provided the funding to make this research possible. Dr. Magley for his continued patience and his desire to meet with me as often as I needed, which was probably more often than I probably should have, but it helped a lot, helped me a lot. Dr. Howell and Dr. Todd, for all the time that they had put in from their busy schedules to help me in this work. Some undergraduate students, which have been very vital. Amanda Pouet, who is the one that built and programmed the force deflector tester that we used to test the rough. Most of all, Isaac for making everything that I passed around here out of copper. Designing how they would be built, designing the test fixtures and so forth. And Nathan Llewellyn, who also helped in fixing this prototype to the polypropylene board. Quentin Anton and Holly Greenberg, especially Quentin, helped me a lot in the FEA and in reviewing my work, and also Holly has spent many hours in reviewing the Journal of Mechanical Design paper I talked about previously. My wife, who's made all this possible, whose love and support has sorry, helped me come here each day and give me the ability to wake up really every morning. I'm sorry. Anyway, I don't get emotional like this usually. And my Heavenly Father, who is indeed the main person to do for all that I've been able to do. Any questions?
Show us that last slide again.
Okay.
Great man.
Maybe we should have it, deflect this
Devin, that's very nice, thank you.
Thank you. Sorry for getting.
I'd like to open the presentation then up to questions from our audience. You have one here, just raise your hand, Devin can handle this.
When you talk about off-axis stiffness in these,
Mhm.
it seems like you'd have a different stiffness in one direction than another, simply by, I mean, if you think of a tape measure, and you bring it out, it'll
Mhm.
buckle in one direction, but if you flip it over, it'll be relatively stiff. Have you investigated that in this, or?
I did look at both directions of bending, and according to ANSYS, they were pretty much the same. It's close enough that I couldn't tell the difference. That was a good question. The radius that I have in here is a full, well, it's supposed to be a full half circle. So maybe that's, tape measure isn't, so maybe that's the difference.
That's a good question, though. We didn't really mention.
You think having it, what you're saying is then, if you have less than a half circle, that would make the difference, or do you think the difference might be between ANSYS and what you actually have is based upon something else?
I think having the arc length from a half circle to smaller would make a big difference in that effect. I really do. I draw that conclusion on. I did have to do an ANSYS analysis on the members here that I did curve, which of course, as you see, are not a full radius, a full half circle, and they're not near as stiff as the top side.
Well, maybe that's a new chapter 7 to see.
Sorry.
Could you go back to slide 16, Evan?
Yes.
Sorry that the phone rang
Oh, it's okay.
in the middle of some challenges.
No problem. Let me advance it here.
You mentioned that the end that was not fixed, you considered to be infinitely rigid.
Yes.
Is that right?
That's
What would
right.
happen if you chose some other boundary conditions? What do you feel that would do in terms of differences? Because it is an infinitely rigid, it's somewhere between that and something else.
Move on to slide, Devin, where you show the 3 nodes you locked.
Okay. I
There you
used some of Dr. Chase's knowledge on these boundary conditions, and he was telling me that if I didn't make it infinitely rigid and just constrain this point to where it didn't translate, you can obviously tell what's going to happen. It's just going to rotate right here and deform on the end. If I didn't make it infinitely rigid, I think that the prototype wouldn't have matched up as well, because even though in the prototype it wasn't infinitely rigid, with the low torque that I put on the prototype, it essentially was, in respect to how much torque I would have needed to deform this area much.
You didn't try putting a crimped piece on the end to stiffen it to see whether or not the interaction would be different?
I-
Any more matched to what the analysis for the analysis that you did?
I didn't. I guess the main reason behind that
Yeah, let's look at the analysis match though.
is because when I saw how well it matched, I didn't feel a need to take the time to do that.
Now, Devin, seems like when we first did that one, you didn't use that exact boundary condition,
I didn't.
right? And then we got the results back and said, whoa, something's wrong here, right? Remember that? And you-
Yes.
Yeah.
I had
Took
the,
a while to find
I did, the one that I showed there. It did take a while to finalize on that.
The first did, we just held the center, and then as it turned, what it would do is it would twist.
that.
Yeah.
Because of shear is the same.
Yes, because the shear it around, and we said, well, it really, we should be modeling with a big chunk out there, right? Went to this boundary condition. Other questions? I think everybody in the lab has seen this a few times,
Yes.
even yesterday, so. All right, well, I think more applause is in order for Devin. And how about we excuse you all while we grill Devin for just a bit?
Should I leave the PowerPoint?
Yep, that'd be great.
Oh, yeah, turn,
Take the temperature.
yeah, turn the camera off here.
Oh, yes.
Some language just should be recorded.